Okay, so it's now recording. So let's get started. So I'm just going to continue where I left off. So we are continuing 7.2.3 from last class, which is on multivariate probability density functions. Okay, so last class I defined the multivariate probability density function. So quickly, I suppose I could show you that again. Just get this out. Okay, 24. Here we go. Okay, so last class, which is a whole lot. Homework 9 and 10. If there's any questions, there weren't any questions. So I defined the multivariate probability density function last class, right? This was the definition. If there's an integrable function f such that this probability is equal to this, function f is the multivariate probability density function for the random variables, right? Okay, so we had this definition here. And so if there's two random variables involved, it's called a joint probability density function. Okay, and so we talked about some properties of it. Okay, so that was basically the end of last class. Okay, that's my computer bugs out. Okay, so we had that definition from last class, and we talked a little bit more. We talked about four important facts about it. Okay, so we also talked about a few facts pertaining to that. Okay, so now to continue, we're going to start with an example. So let's do example 7.7. So suppose x, y are continuous random variables with joint probability density function f of x comma y, which is equal to this function. So there we go. Okay, so it's equal to 1/2 x e to the negative y for 0 less than x less than 2 and y positive. Okay, also it's 0 elsewhere. Okay, so A, find the joint cumulative distribution function x, y. Okay. So let's look at a few cases. So case 1, for case 1, we have for x greater or equal to 0 and any y, so that goes from any real number y. Okay, and so here we're going to talk about the joint cumulative distribution function of x and y, capital F. So it's going to be equal to this double integral. So it's going to be the double integral from negative infinity to y, and then the integral from negative infinity to x of f of s comma t ds dt, which is equal to the double integral again. Is equal to the double integral of 0 ds dt. Okay, so This is x less than or equal to 0. Okay, so x less than or equal to 0, that would mean that this f of x comma y is 0 there, right? And so that would mean that you now have 0 as capital F. Okay. Case 2, we have now instead those x values. We're going to change the x value. So now we're going to have from negative for negative infinity less than x less than infinity. Now we're going to now have, okay, we're going to have y less than or equal to 0 for case 2. And so for case 2, we have that the cumulative distribution function, capital F, is equal to, okay, so we have that. And then it's going to equal to what this is. And here, it's still 0. And so you get 0. And so that's because y is less than or equal to 0, right? And so if you're going up to y that's at most 0, little f there is 0. So you get 0 here. So case 3, we need something that's in neither of those. So for 0 less than x less than 2, y positive. Okay. And so for that situation, we have capital F of x comma y is equal to this. Okay, and so then this is equal to, well, for that range of values, right, we have, this is f, right? So here we're using s as a dummy variable. And so that means that we're going to have 1/2. We're going to have 1/2 se to the negative t. That's just 1/2 x e negative y, but we're using s and t instead of x and y. Okay. Good. And so then we have that. Okay. And so now, okay, so now we can separate the two variables. And so we're going to have the def here. And the first thing, we're going to have the def integral from 0 to y. That's because we only have, for y positive, that little f is non-zero. And so we only have to consider the y's that are positive, right? So we can go, instead from negative infinity to y, we're going from 0 to y. And then our dummy variable is t. This is e to the negative t dt times the def integral from 0 to x of 1/2 s ds. Okay, and so then that is equal to 1/4 x squared. So you just evaluate this integral, and you get 1/4 x squared, and then you evaluate the other integral, and you get 1 minus e to the negative y. Okay. Okay, so then capital F of x comma y is equal to this for this range of x and y values. Okay, that's case 3. And so to exhaust all possible choices of x and y, we have our last case, case 4, which is for x greater than or equal to 2 and y positive. Okay, so for x greater than or equal to 2, y positive, we have this integral. And so then we have that we have our function 1/2 se to the negative t. But now, instead of going from negative infinity to y, we're going to go from 0 to y. And now instead of from negative infinity to x, it's going to be from 0 to 2, because those are the range of x values here. So we're going to go from 0 to 2. Because if x is going to equal to 2, we're going to start at 0 and end, go all the way up to 2. Okay, because our original PDF is only non-zero for x values between 0 and 2. Okay, and so then just okay, and then that's equal to, and then okay, and so then that's equal to definite integral from 0 to y of e to the negative t dt times definite integral from 0 to 2 of 1/2 s yes, and that's equal to 1 minus e to the negative y. Okay, so now in those four cases, we found the cumulative distribution function capital F of x comma y. Right, so it was a matter of most of the time deciding where we needed to integrate. Okay, in these first two cases, we had the little f was 0 throughout, and so the integrand was 0 in cases 1 and 2. And in cases 3 and 4, we had to then just restrict the where we were integrating. Okay. Okay, part B. Find the probability that 1 is less or equal to x, less or equal to 2, and 3 is less or equal to y, less or equal to less or equal to 4. Okay, so oh, sorry. Okay, first we want to find the probability that x is less or equal to 1, and y is less or equal to 2, and that's equal to capital F of 1 comma 2. That's what that means. It means x at most 1 and y is at most 2. And so from the way we define capital F, we have x is 1 and y is 2. So that falls into case 3. And so this is the expression for capital F there. Okay, but here x is 1 and here y is 2. So just plug in those values. And so what you get is 1/4 times 1 minus e to the negative 2. Okay, and that's the answer for that one. For the next one, we want to find the probability that 1 is less or equal to x, less or equal to 2, and 3 is less or equal to y, less or equal to 2. Okay. So for this, we're going to integrate again. And so we're going to double integrate. So on the outside, we're going to integrate with respect to y. So for y, we're going to go from 3 to 4. From 3 to 4, and then this is going to be the integral with respect to x is going to go from 1 to 2. And so we have f of x comma y dx dy. Okay, and so then we have that, and this is equal to, so we have this integral. Okay, and it's now our f. So now our f function, our little f function, is 1/2 x e to the negative y. Okay, so that's our PDF dx dy. And so when you integrate that, when you calculate that double integral, you get 3/4 times e to the negative 3 minus e to the negative 4. Okay, and so that's that probability. Okay, another example 7.8. Let capital X and capital Y be continuous random variables with joint probability density function joint probability density function f of x comma y, which is equal to which is equal to 2xy plus 3/2 y squared for 0 less than x less than 1, 0 less than y less than 1, and 0 elsewhere. Okay, let capital C be the region of points x comma y in the plane such that x plus y is strictly less than 1. Find the probability that x comma y is in C. Okay, so let x and y be continuous random variables with joint probability density function f. Find this way. And let C be the region of points x comma y in the plane such that x plus y is less than 1. Find the probability that the point x comma y is in this region C. Okay, so solution. So first, well, before we look at the solution, we're going to go to the whiteboard. I'm just going to point out the region given by that inequality, x plus y less than 1. So if you have x plus y less than 1, right, that's equivalent to saying y is less than 1 minus x, right, subtracting both sides by x. And so when you graph this inequality, all the points that satisfy that inequality, then 1 minus x, if you were to graph y equals 1 minus x, you would get this line. Okay, this would be the line y equals 1 minus x. It's y equals negative x translated up by 1. You could think of it as y equals negative x plus 1. It's the same thing. And so you would get this, right? This intersection point has y coordinate 1, right? And this x-intercept has x coordinate 1. Now, if y is less than 1 minus x, then that's really representing all the points below this line. And so the blue shaded region, that represents all the points x comma y that satisfy the inequality y is less than 1 minus x. Okay? Okay, so the shade region is the region satisfied by this inequality. It's not, I'll do it this way. My hand, I guess. Okay, so all the points x comma y that satisfy the inequality, that all the points in this blue shade region satisfy this equality. Points that are not shaded blue, points on the line and points above the line do not satisfy it, right? Points on the line, y equals 1 minus x, that would be equal, it would not satisfy strictly less than. So only points below the line satisfy that equality. Okay, so let's go back to now here. So when I find this probability, so let's keep in mind that shaded region. blue shade region. So we have points x, comma, y that are in the region C, probability of that. And it's equal to double integral over the region C of f of x, comma, y dx dy. So you want to integrate that shaded in blue region. So also let's note, let's go back to the whiteboard for a second. Now, the PDF I gave you, let's go back to the notes. This is the PDF I gave you, right? It says for x between 0 and 1 and y between 0 and 1, the PDF is this, and it's 0 everywhere else, right? So we only really care about x, y's that satisfy these inequalities, right? And so if you look at the whiteboard again, I'm going to shade in purple, light purple, the points that satisfy those inequalities and are in the blue region. Only this section, right? This is the only part that satisfies those inequalities. It's not on the line. It's in between these lines. It's inside the triangle. Those points, those purple points. Those are the points where not only is it in the region C, but f of x, comma, y is not necessarily 0. Okay, so we only need to integrate here. Okay, below this line and in the first quadrant. Okay, so here when we take this double integral, we're only going to want to integrate there. And so first considering with respect to y, we're going to go from 0 to 1. And now if we integrate with respect to x, it's going to be from 0 to 1 minus y of 2xy plus 3/2 y squared. This is dx dy. Okay. So if we have 0 to 1 minus y and 0 to 1, that, right? So 0 to 1 minus y. So if you look at the okay, so actually what we're doing is we're integrating here. So we're integrating this way, ironically. The approximating rectangle is horizontal. And so we're looking at this line. Instead of y equals 1 minus x, we're thinking of it as more as x equals 1 minus y. It's either below the line or to the left of the line, right? It's the same region. It's just how you're integrating. This is x equals 1. It's also x equals 1 minus y. And so when we integrate, we're integrating from x equals 0 to x equals 1 minus y. From x equals 0 to x equals 0. So we're going from x equals 0 to x equals 1 minus y, and then from y equals 0 to y equals 1. So make note of that. It goes from 0 to 1 minus y, the x values, and then from 0 to 1, the y values. These horizontal rectangles sweep from the bottom to the top part. Okay. So it's 0 to 1 minus y for x and 0 to 1 for dy. Okay, and so then you integrate that. And so the hardest part is done, and now it's just a matter of integrating. And so you have the def integral from 0, 1 of, now what's that first integral, which is 1 minus y squared y plus 3/2 times 1 minus y squared dy. And that's equal to 5 over 24. Okay? And so we now found the probability that our point is in the region C. Okay, and so that's example 7.8. Okay, so next is 7.2.4 on marginal distributions. So let's talk about definition 7.4. Okay, so let x, y be discrete random variables with joint probability function f of x comma y be the marginal probability functions of x and y respectively are given by following f sub x of x is equal to the sum over all possible values of y of f of x comma y. Okay. Note that f sub x of x is equal to the probability that capital X equals little x, which is equal to regular f of x. Okay. Okay, so this is about the marginal probability density functions of x and y. Okay, so this is the marginal probability function of x because this subscript x here. This is the marginal probability function of y. Okay, and then this is equal to the sum over all possible values of x of f of x comma y. Okay, and note that f sub y of y is equal to the probability that y is equal to some x little y, which equals f of y. Okay, so by finding f sub y, y is the same as summing over all possible values of x of f of x comma y. Part B, let x, y be continuous random variables with joint probability density function f of x comma y. The marginal probability density function of x and y respectively are given by f sub x of x, which is equal to the integral from negative infinity to infinity of f of x comma y dy, and f sub y is equal to the integral from negative infinity to infinity of f of x comma y dx. Okay, so this is for a discrete, right? This is for discrete, this is for continuous. And note that probability of a less than x less than b is equal to the probability that a is less than x less than b and negative infinity is less than y less than infinity. And that this is equal to, the integral from negative infinity to infinity infinity of the integral from a to b of f of x comma y dx dy. And this is equal to the double integral, except you switch the order of integration. This is going to go from a to b. This is going to go from negative infinity to infinity. This is going to switch, so it's going to be 2y dx. Okay, and so you're going to integrate this first. And then the other one. Okay, so this is equal to the integral from a to b. This is the outer integral here. Well, this integral right here is f sub x of x. This is f sub x of x. This guy right here. See that? In the parentheses of this. So that's dx. That dx. Okay. And so what this implies that the probability of a less than x less than b is equal to this integral. Okay. And so now we have this equation for the probability of x values in an interval. Okay. So example 7.14. Find the marginal probability density function of random variable capital X of example 7.5. Find the probability that X is strictly greater than 2. Okay. Solution. The joint probability density function of x and y is f of x comma y, which is equal to e to the negative x times e to the negative y for x greater than 0, y greater than 0. And it's 0 elsewhere. Okay, so the solution. Okay, so that means that f sub x of x is equal to the integral from negative infinity to infinity of f of x comma y dy. And so that's equal to the following. So you just integrate this thing, right? So you integrate from negative infinity to infinity of e to the negative x, e to the negative y dy, which is equal to e to the negative x for x positive. And it's 0 elsewhere. Okay. So the probability that x is greater than 2 is equal to the integral from 2 to infinity of f of x dx. And that's equal to the integral from 2 to infinity of f sub x of x dx. That's equal to the integral from 0 to 2 of e to the negative x dx, and that's equal to e to the negative 2, which equals 0.1353. Okay, and so you just plug in this PDF here for x positive at 0 elsewhere. And so for x greater than 2, since 2 is greater than 0, you're just integrating from 2 to infinity. And so you get, okay. All right, so the next section is 7.2.5. And it's on conditional probabilities, or conditional distributions. Okay, so we're going to let x, y be discrete random variables. Okay, so we have the probability that x equals x naught and y equals y naught. Sorry, probably x equals x naught given y equals y naught. So then that's equal to the probability from conditional probabilities, the probability that x equals x naught and y equals y naught divided by probability that y equals y naught. Okay, and so then this is equal to f of x naught, comma, y naught, divided by f sub y of y naught. Okay, so this is provided that p of y equals y naught is greater than 0. Okay. Okay, so we have f sub x of x given y naught. This is equal to the probability that x is equal to little x given that y equals y naught. This is equal to f of x comma y naught over f sub y of y naught. Okay, from this definition, from this here. Okay, and so we just have x comma y naught, and we have the same denominator here. And so this is the conditional probability function of capital X given y equals y naught. Okay, so this is the probability x is equal to some value given that y is equal to some value. Sorry, excuse me. F sub x given y is equal to f of x comma y over f sub y. Then f sub y of y given x is equal to f of x comma y over f sub x of x. Okay, and so this left equation is if f sub y of y is positive for all x. And the right one is if f sub x of x strictly positive for all y. Okay, let's assume example 7.15. Let x, y be continuous random variables of example 7.8. Okay, so let's do part A. Okay, so so example 7.8 is what we just did. Up here, this one. Okay, so all this is what we're working with in this example. Okay. Okay, so let's go back here. So for A, we have f sub capital X of x, which is equal to the integral from negative infinity f of x comma y dy. And that's equal to so it's equal to f integral from 0 to 1 of 2xy plus 3/2 y squared dx, which is equal to I plus 3/2 y squared. This is for 0 less than y less than 1. Just want to put this on one line here. Okay, it's not working. Okay, so it's going to have to be like this. And it's 0 elsewhere. This was the PDF in that example. And it went from 0 to 1. So if you have f sub y of y, it's equal to the integral negative infinity to infinity of f of x comma y dx, and that's equal to two possibilities, right? So you get okay, so this is with dy here. That's dy. Oh, okay, sorry. That's dy, and this is x plus 1/2. Okay. For 0 less than x less than 1. Okay. Okay, that's good. This one is the def integral. Is this def integral with respect to x? Okay, so now it's going to be 0 to 1 of 2xy plus 3/2 y squared dx, which is equal to y plus 3/2 y squared, 0 less than y less than 1. And 0 elsewhere. Okay. Okay, so if you're integrating with respect to y, you find this integral for x is between 0 and 1. And if you're doing f sub y, you're integrating with respect to x from 0 to 1, and you get this expression of y, for y between 0 and 1. Okay. So that's A. And then for B, we have for 0 less than y less than 1, we have f sub x given y, which equals f of x comma y, divided by f sub y of y. Okay, and so this is equal to following. So for x between 0 and 1, you get 2xy plus 3/2 y squared for f of x comma y, divided by y plus 3/2 y squared. Okay, the PDF f of x comma y is this, and we found f sub y of y. It's equal to y plus 3/2 y squared. So you just plug me in. Those two things are here. And this is equal to the fraction 2x plus 3/2 y divided by 1 plus 3/2 y. It's just dividing the numerator denominator by y. And this is for 0 less than x less than 1. And it's 0 elsewhere. Okay. Next, for 0 less than x less than 1, you have the f sub y of x given y is equal to f of x comma y divided by f sub x of x. And that's equal to, so you're going to plug in what f of x comma y is. In the numerator, it's 2xy plus 3/2 y squared. In the denominator, it's f sub x of x, which we found. F sub x of x is x plus 1/2. So in the denominator, you have x plus 1/2. And this is for 0 less than y less than 1. And it's 0 elsewhere. Okay, so now we found it for y between 0 and 1 and for x between 0 and 1. Okay. For part C, let's find the following probabilities. Let's find the probability that 0 is less or equal to x less or equal to 0.5. Okay, so that's equal to the def integral. Zero 0.5 of f sub x of x dx. This is equal to second from 0 0.5 x plus 1/2 dx, and that's equal to 0.375. Okay, so you're just integrating from 0 to 0.5 of f sub x of x, you get that. Okay. Next, if you find the probability that 0 is less or equal to y, less or equal to 0.4, this is equal to the def integral from 0 to 0.4 of f sub y of y dy. This is equal to, where's my cursor? Okay, now so it changed. And this is equal to, you see, okay, we're back. Okay, this is equal to difference from 0 0.4 of f sub y of y, which is y plus 3/2 y squared dy, and that's equal to 0.112. Okay, so we found those two probabilities in C. In part D, we're going to find the probability that 0 is less than or equal to x less than or equal to 0.5. That's given y equals 0.3. And this is equal to the def integral from 0 to 0.5 f sub x of x comma y. Sorry, f sub x of x given 0.3 dx. So this is equal to the def integral from 0 to 0.5 of 2x plus 3/2 times 0.3 over 1 plus 3/2 times 0.3 dx. That's equal to 0.3276. Calculate it. Okay, so that's D. And then E is the probability of 0 less or equal to y less or equal to 0.4, given that x is equal to 0.2. And so that's equal to def integral from 0 to 0.4 of f y given at x is 0.2 dy. And so that's equal to the def integral from 0 to 0.4 of 2 times 0.2 y plus 3/2 y squared. So this is f of x comma y. And then you're plugging in for x 0.2. And then denominator is going to be x, which is 0.2, plus 1/2. So it's that. dy. Okay, when you integrate that, that's equal to 0.0914. And that's E. And that example is over. Okay, so let's keep going. So you have 7.2.6, which is on the multinomial distribution. Okay, so definition 7.6. Let n and k be positive integers. Let p1 up to including p sub k be numbers such that the sum from I equals 1 to k of p sub I is equal to 1. And each piece of I is between 0 and 1 for all I, well, for I from 1 to k. The multinomial probability function f is defined by f of x sub 1, x sub 2, x sub k, which is equal to n factorial over x1 factorial, x2 factorial, dot, x sub k factorial, multiplying all them out. There's b1 to the x1 times p1 raised to the x1, p2 raised to the x2, dot, p sub k raised to the x sub k. And this is for integers x1, x2, dot, x sub k greater or equal to 0, such that the sum from I equals 1 to k of x sub I is equal to n. Okay, so that's the definition of what's called the multinomial probability function f. Okay. Okay, so the probability that probably of exactly x sub I occurrences of the outcome a sub I from 1 to k is equal to the probability that x sub 1 is equal to little x sub 1, x sub 2 is equal to little x sub 2, and so forth. X sub k is equal to little x sub k, and that's equal to n factorial divided by x1 factorial, x2 factorial, x sub k factorial, p1 to the x1 P2 raised to the X2 dot 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 P sub K raised to the X sub K. Okay, so if each of the outcomes A sub I is occurring X sub I times, then right, the probabilities of each of them are P sub I. And so them occurring X sub I times means that P sub 1 to the X1 times P sub 2 to the X2 times dot 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 times P sub K to the XK, right? That's multiplying, the probability X sub 1 times X sub 2 times and so forth, right? The P sub I's. You're multiplying P sub 1, X sub 1 times, P sub 2, X sub 2 times, P sub 3, X sub 3 times, and so forth. P sub K, X sub K times, right? But you can arrange them. You can arrange how the occurrences of these things. And so that's n factorial over this. So this expression is telling you how many ways there are common combinations of those things. Okay. All right. Let's keep going. So 7.2.7 is the bivariate normal distribution definition. Definition 7.7. Let mu1, mu2, sigma 1, and sigma 2, and p be constants with sigma 1 positive, sigma 2 positive, and negative 1 less than p less than 1. The function f of x comma y is equal to, so I'm defining a bivariate normal probability density function. And so this is the function. So I'm going to write it out. It's very long. It's e to the negative 1 over 2 times 1 minus p times x minus mu sub 1 divided by sigma sub 1. This quantity raised to the second power minus 2p times x minus mu 1 over sigma sub 1 times y minus sigma sub 2 over sigma sub 2 plus y minus sigma sub 2 over sigma sub 2 squared. This, what's being squared is just this thing in the parentheses, right? There's the thing in the brackets. There's this squared minus 2p times this plus this squared. Follow order of operations. It's e to negative all of that. And then in the denominator, it's 2 pi sigma 1 sigma 2, which is square root of 1
minus p squared. This is for negative infinity less than x less than infinity, and negative infinity less than y less than infinity. That is the bivariate normal probability density function. Okay, that's the bivariate normal probability density function. All right. And that's definition 7.7. Okay, nearing the end. All right, 7.3. Independent random variables. 7.3.1. Definition of independent random variables. Definition 7.8. Let x1, x2, xn random variables, discrete or continuous, with probability functions f sub 1 of x1, comma f sub n of xn, respectively, and multivariate probability function f of x1, comma comma x sub n, the n random variables are independent if f of x1, x2, up to including x sub n is equal to f sub 1 of x1, f sub 2 of x2, f sub n of xn. For all values of x1, x2, x sub n of capital X1, comma capital X2, comma capital X, capital X sub n, respectively. Except at points of discontinuity. Okay. Okay, so they're independent if this equation happens. If you can express this function as a product of these. All right, example 7.17. Let's make x1 the value on the die. So you roll a die, six-sided die, and x1 is the value on that die. x2 is going to be the number of heads from one coin flip. So that's x1 and x2. Now f sub 1 of x1 of x1 is equal to the probability that x1 is equal to little x1. Okay, and so that's 1/6, right? For all values of x1. So that's for x1 equal to 1, 2, 3, 4, 5, and 6. Okay. F sub 2. F sub 2 of x2. F sub 2 of x2 is equal to the probability that x sub 2 is equal to little x sub 2, which is equal to 1/2. And this is for x2 equal to 0 or 1. Okay, so that implies, okay, so that implies that f of x sub 1 comma x sub 2 is equal to 1/12 which equals to 1/6 times 1/2 which equals f sub 1 of x1 times f sub 2 of x2 for all x1 comma x2. Okay, so f of x1 comma x2 is equal to 1/12, which is equal to 1/6 times 1/2, right? Which equals the f1 of x1 times f2 of x2 for all x1 x2. And so therefore, x1 and x2 are independent. And x2 are independent. Okay. And let's finish this up. Just give a few more minutes and we're done. So x1, x2 independent is true if and only if the probability of A intersection B is equal to the probability of A times the probability of B. Okay, where here you can think of A as being equal to x1 you can think of A as being x1 equal to little x1. You can think of B as being y2 x2 equal to little x2. Okay, so the probability that x1 is equal to little x1 and x2 is equal to x2 is equal to the probability that capital X1 equals little x1 times the probability capital X2 equals little x2. Okay, so that's this equation is saying. Okay, with this A and this B. Okay, and then we're just about the end of everything. 7.3.3 independent random variables derived from independent experiments. Okay, so part A. E is the experiment. S is the sample space. Capital E. X is the random variable on capital S. Experiment E is repeated n times under identical conditions. The random variables x1 to xn are independent random variables if x of I is the random variable on the ith performance of E from 1 less or equal to I less or equal to. Okay, so if you just repeat the same experiment n times, and x1 to xn are their respective independent or their respective random variables, they're independent. Okay. Okay. B. If you have E1 to En, experiments are separate and distinct experiments. The outcome of E sub I is no way dependent on the outcome for the outcome of E sub j when I does not equal j. For E sub j when I is not equal to j. S1 to S sub n. S sub n are sample spaces for E1 to En, respectively. If x1 to xn are random variables defined on S1, Sn, respectively, then they are independent random variables. Okay, in the very last sentence, if x1 to xn satisfy A or B, then they are independent. Independent by definition. 7.8. Okay, and that is the end of the course. Okay, that's it. Well done. Okay, so there is one more homework. So what I did was I posted the solutions online. So if you go to the homework section, if you go to the homeworks tab and you see the homeworks there, underneath the homeworks, you'll now see the solutions to the last homework assignment, homework 11. Okay, so what I want you to do is do homework 11. Okay, the answers are on Blackboard. The answers and solutions are on Blackboard. Okay, on the homework section. Okay, so if you go to the menu bar and you go to homeworks, you have homeworks 1 through 11 as normal. Underneath that are I typed up the solutions to all the problems in homework 11. Okay, so you can refer to that to study. Okay, and don't forget, remember that test 2 in this class, test 2 is on Wednesday, May 12th during class, right? Which is from 8 p.m. to 9:15 p.m. Right? And we're going to use the usual Zoom link to attend normal class. Just use the usual Zoom link to attend the exam. Okay, so that means the Zoom link you used today to join class in every other day, same link to join the Zoom session for this test, and it's during class from 8 p.m. to 9:15 p.m. Okay, the structure will be very similar to the other exam. Okay, and also remember the review sheet. Review sheet is on Blackboard. The solutions to homework 11 are also on Blackboard. Okay, not just the answers, but I wrote up how the explanation of. I wrote part of the solution, part of the explanation, a good deal of the explanation of all the problems. Okay. Okay, and so that's that. And also very important, remember that the final is on the last day of class on May 17th. So that's reminding you it's a week from today, during class, also during class. So that will be, so also during class from 8 p.m. to 9:15 p.m. Show up on time. Okay, the class is going to start right away, very quickly. So make sure to be on time. Okay, so after the third exam, after the second exam on Wednesday, this Wednesday, I will stay. Okay, online, and you can ask me questions if you want about the final. If you want me to go over things to help you with, I will stay after class on Wednesday to help you with the final. Okay, so if you have questions about the final is only during class time, so you know it'll be for the time of regular class day. Yeah. Okay, so it'll be during class, so it can't be 2 hours, right? Because the class is only an hour and 15 minutes. Okay, so but yeah, so if you want to stay, if you want me to answer questions and help you about studying for the final, you can stay after class on Wednesday and I will go over it. Also, I will return your grades for the second exam before you take the final. Okay. Okay, so also you will get your grades on the second exam before the final. Okay, you'll probably get them, way before. So, well, not wait. What I mean is you'll get them before the final, so you'll know your grade on the second exam. You should know it before the final. Okay. The final is on Monday, right? So exam 2 is on this Wednesday and the 12th, and then the next one is Monday, and that's the final, right? And then that's the last day of class, and that's it. Okay, so there's nothing after the 17th. 17th is the last day, so you have to be here for that. Somebody said there were religious reasons why they couldn't make class on Wednesday or Monday. If there's religious reasons why you can't make an exam or something else, you have to email me, okay? Speak to me directly about it. Okay, so make sure to email me. Don't tell me 5 minutes before the exam. You should have told me already. If there's something that you need to tell me about, you tell me back as soon as possible. Okay, email me about it. Okay, I think that's everything. Anyone have any more questions about anything? Any of all this stuff? Lots going on. Any more questions? Any questions? Okay, so Rajesh, you know, right? So there's a test 2 exam on Wednesday, and the following Monday is going to be the final, right? So I don't know what you mean by what we have class in mind. That doesn't make sense, that question, right? So we have the second exam this Wednesday, and the final is the following Monday. right, on the 17th. Okay, so there is still, we're meeting those days. Okay, if there's no more questions, we can end now. Okay, so have a good night, everybody. Bye. You're welcome. Good night. Thank you being here. Good night. Bye.